Hello dear students, my name is Gaurav Saraf and I am the chemistry faculty at Allied Super 40 Coaching Institute. We are a coaching institute which provides coaching for IIT, JEE and NEET competitive examinations. I am a B.TECH from IIT Kanpur and I hold a total of 3 years of experience in teaching into IIT, JEE and NEET competitive examination. I am a B.TECH from mechanical engineering and have taught students who have cleared in IIT, JEE and NEET. So yeah, and today we are going to learn about a very important topic of chemistry, physical chemistry, which is called thermodynamics. Can you stop it? So today we are going to learn about a very important topic which is called thermodynamics. Now, before we actually get into this particular topic, what I really want you to know the importance of this topic. So, if you, I know many of you might be preparing for engineering examinations, and when you actually go into engineering and say if you select engineering subjects like aeronautical engineering, mechanical engineering or electronics engineering per se, thermodynamics will play a very important role and you will like study the entire 4 years. Thermodynamics will not leave you until you graduate if you select any of these engineering examinations. Even in medical line, right, if you go for MBBS or higher research, then thermodynamics becomes a very important part if you especially go for specializations like surgery or if you go for research on heart or veins or so on. So this is a very important topic for you to clear base on, and so that it not only helps you in clearing your competitive examinations, but at the same time also builds a base for clearing your for your future studies and for your career perspective as well. Now to start with, let me ask you guys, what do you understand by the term thermodynamics? You don't have to get into physics or chemistry or anything of that sort. Simple English, what does thermodynamic represent, or what do you feel when you hear the term thermodynamics? You can also talk about it. What do you think when you talk about thermodynamics, or what do you feel it is? Study of attraction of molecules. Okay. Anything else? Okay, so let me help you with this. Before we get actually into the technicalities of this, it's very important to understand what does this term actually mean. So this part of the term, right, thermo, you might get an intuition that this represents in some sort heat or energy, right, related to heat or energy. And what does dynamics relate to? Dynamics relate to movement, or in plain English, what does dynamics mean? It means movement. So what does thermodynamics actually mean? It means movement of energy. Okay. So in total, what we are going to talk about in thermodynamics is movement, various processes which happen because of the movement of energy from system to surrounding. Now pay attention to the words system and surrounding, and keep these in mind because these are two things we will be talking about very shortly. So what did I say? Do you want to note it down? Thermodynamics talks about the movement of energy from system to surrounding. System to surrounding. Okay. Did you understand this? Okay. Have you noted it down? So now, two most important terms to understand in the context of thermodynamics, as I mentioned, are system and surrounding. System and surrounding. So the entire setup where you are performing the where you are performing the process of thermodynamics, that is considered as your system. So I'll also explain it to you with an example, but for time being, understand that the setup, right, where the thermodynamic process is performed, right? Process is performed is your system. Okay, so that system in focus, basically the apparatus in focus is your system, and what is surrounding, everything else in the universe is your surrounding. Okay, now if we were to take an example on this, right, so suppose, say I have a beaker in lab, right, and what I am doing is I am heating water. I am heating water. Now, if I have to study this particular system, this particular apparatus, and the processes that are happening in this will be my system, right? And what is surrounding? Everything else in the laboratory around this, everything else is my surrounding. The air around this, or everything else is my surrounding, right? So just to recall the definition of thermodynamics, basically system and surrounding. So thermodynamics essentially refers to the process of energy movement from system to the surrounding, where system is the focus in which the thermodynamic process occurs, and surrounding is everything else which is surrounding the system. Okay, did you understand this? Okay. So, now if you have understood this, another important thing to understand is boundary. Okay, boundary or wall or interface. Now, can you tell me what do you understand by this? We have talked about system, we have talked about surrounding. What might this refer to? Correct, exactly. So the interface which is separating the system from the surrounding is called the boundary. We generally refer to a boundary. That's why it's called a wall. It might be called as an interface. Okay. So for example, if I take a vessel and say there is a piston on the vessel, right? You can take any example, but I'm taking this example. And there is gas, some gas here. Okay. Now, can you tell me what will boundary refer to? So, boundary will refer, as I already mentioned, boundary is any interface separating system from the surrounding, right? Now, there might be different kind of boundaries that we'll talk about, we'll go into details of that. But before that, in this example, can you tell me what could be a boundary? This could be a boundary, right? Because this is a surrounding, this is your surrounding and this is your system, right? This entire thing. So, this could be boundary. What else could be boundary? Can you tell me? Yes, the beaker walls, right? These walls. These could also be boundary, right? Right? So these are different kind of boundaries. We'll just talk about it very shortly. But did you understand that what boundary essentially refers to? Did you understand? So boundary essentially refers to any line, any interface which separates the system and the surrounding. As simple as that, right? Now, as I have been mentioning, there are different kinds of boundaries that we'll talk about. Now, so the first segregation of boundary is it, or let's talk about walls, or I'll write wall, real and virtual. So first type of segregation of boundaries is real boundary and virtual boundary. Can you tell me, these are very intuitive things. So can you tell me what real boundary would refer to? So let's take again a beaker with water. Water is there. This is a beaker and we are hitting it. Now, can you tell me what will be a real boundary and what will be a virtual boundary? Yes, in plain English, if you think about plain English, yes. So, what one of the students is saying is basically real boundary is one which we can see through our eyes, and virtual is which we cannot see through our eyes. But if we go into details, that is not exactly the case, although that also holds true. So, I'll tell you what real and virtual boundary means. So, there is whenever through a boundary you cannot transfer matter. Okay, matter cannot be transferred. That is a real boundary. Yeah, and a boundary through which matter can be transferred is called a virtual boundary. You can note it down, I'll explain in a bit. Matter can be transferred is a virtual boundary. Okay, this is a virtual boundary. Now, if you see carefully, right, this is a beaker. What do I mean by matter? Matter means substance, right, which is there. So here the matter is water. Now, if you see very carefully, this particular boundary, this is a real boundary. Why? Because water cannot come out of in and out of this, right? Essentially, matter cannot be transferred from this through this boundary, right? Whereas if you see this boundary, there is no boundary. There is just a layer of water, and then there is air separating this. So from this, water can come out as well, right? So the matter can be transferred. So essentially, this is the definition of real and virtual boundary. In real boundary, the matter cannot be transferred from the system to the surrounding or vice versa. Whereas in case of virtual boundary, matter can be transferred to and from the system. Right? Did you understand this? Do you want to note it down? Okay, you can note it down. So maybe I'll write a more refined definition, which is matter cannot be transferred in and out of the system. Okay, and virtual boundaries, matter can be transferred. Okay. You can note this down. Did you note this down? Everything? Okay. So now, this is one sort of segregation of the boundaries, right, which is real and virtual boundary. Now we will move into another sort of segregation. So second segregation of boundary is we are talking about adiabatic walls. We are talking about diathermic walls. Now, so second sort of segregation of the boundary is the segregation of adiabatic walls versus diathermic walls. Now, what is adiabatic? What does adiabatic wall refer to? So, adiabatic wall refers to where heat cannot be transferred in and out the system. And what dithermic walls refer to? Where heat can be transferred in and out of the system. Right? So essentially what we are talking about is, in adiabatic walls are the walls or boundaries where heat transfer cannot take place between the system and the surrounding, right? Whereas in dithermic walls, heat can be transferred in and out of the system. So if you compare it with the previous case, there we were talking about matter, transfer of matter. Here we are talking about transfer of heat, right? So this is the second segregation. Did you understand this? Let's move to a third segregation, that is rigid walls versus movable walls, right? So can you explain what, this is very intuitive, can you explain like what will be the difference between these two type of boundaries? So movable you can explain, right? What is movable? The wall or the boundary which moves, which can move, right? And rigid which cannot move. So this is basically the boundary or wall which cannot move, right? This is boundary wall which can move. Now let's see an example. So we were talking earlier, we were talking about this example, right? Suppose that we have a piston here and this is some gas, right? Now can you tell me which will be a rigid wall versus which will be a movable wall here? Yes. So this beaker will be a rigid wall, right? And this is a movable wall. So another thing to remember is, in movable walls there can be work done by external pressure. I'll explain in a bit what does this mean. Here there can be no work done. So what I mean is, if you press this piston, if you apply pressure on this piston, you can, if you apply some pressure on this piston, you can do work, right? This will go down, this will compress. There will be some work done on the gas. Whereas if you apply pressure on this rigid walls, there will be no work done, right? Nothing will happen even if you apply pressure. So movable walls, there can be work done by the external pressure, whereas in rigid walls there can be no work done by the external pressure. This is something you should remember. Okay, did you note down? Should I rub it? Okay, so let's revise the different kind of boundaries we learned, because it's important. So what are the different kind of boundaries we studied? First is real and virtual, right? Second is, what is real? Let's just quickly summarize it. What is real? Where matter can be transferred. What is virtual? Sorry, what is real? Where matter cannot be transferred. What is virtual? Where matter can be transferred, right? Second classification is adiabatic, Dithermal, right? Here, heat cannot be transferred. Here, heat can be transferred. What is the third segregation? Rigid, movable. So, here it does not move. This boundary does not move. This boundary moves. External pressure cannot do any work. External pressure does do some work on the substance or the matter, right? So, these are the different kind of boundaries. Now, let's do an example which is a bit tricky, but it's not tricky in the sense, but let's see. So, let's say we have a balloon. Okay, we have a balloon. We have filled it with air. Can you tell me what kind of boundary is this? It's real. Then yes, heat can transfer in and out. So dithermic. Rigid or movable? Movable, yes, because balloons are stretchable, right? So these are the three properties of this one. Now what I do is I make a small hole in the balloon. I make a small hole. Now can you tell me what kind of wall is this? Yes. So this becomes a, now if I make a small hole, what will this become? This will become a virtual boundary. Why? Can you tell me? Because now matter can transfer out of this balloon, right? In and out of the balloon. So as soon as we make a hole in the balloon, it becomes a virtual boundary, right? So this is something important to. So if we go by your earlier definition where you said that real walls are visible, virtual walls are not visible, that won't be true, right? In this case, this wall is virtual, but it's still visible. So the essential definition is through real walls, matter cannot be transferred, whereas through virtual walls, matter can be transferred. So did you understand this? Okay. Now we are done with the discussion on systems surrounding boundaries, walls. We have completed that discussion. Now next important discussion is the different kind of systems. Okay. So what are the different kind of systems? We have three kind of systems. One is closed, open, third one is isolated, right? So we have three kinds of systems: closed, open and isolated. Can you tell me what is a closed system? Yes. So a closed system, as it is very intuitive, closed system is one where matter cannot be transferred, okay, within system and surrounding. Got it? This is a closed system. Matter cannot be transferred in and out of the closed system. Heat can, right? What is an open system? Yes. So, in open system, matter and heat both can be transferred in and out of the system, right? And what is an isolated system then? Yes. Isolated system is one where matter and heat both cannot be transferred in and out of the system. Did you understand this? Let's think of an example. What can be an example of a closed system? Water in a bottle. Water in a bottle. Yes, you can take that. Normal water bottle, right? Normal water bottle. Example. Open system. Any system, water in a beaker, right? Water in a normal water bottle closed, right? Otherwise matter can be transferred. This any beaker, water in a beaker, right? Open beaker. No, beaker. And what will be an isolated system? Think about it, we use it in our daily life. A thermos flask, right? Thermos flask, neither matter not energy can be transferred, right? If you keep water in it, it remains hot as it is. So, thermos flask. Understood? You want to note it down? Done? Okay. Now, next important thing that we'll talk about is a state function and path function. So, these are the two important terms we'll understand what does it mean. So, first we'll talk about state function, then we'll go to path function. Now, state function basically, what does state represent? State represents the current or a particular situation, right? So, what do I say? What is my current state? My current state is that I am teaching, right? That is my current state. So, state represents the condition of the system, whatever our system is, right? Condition of the system at any point in time. Right? That is state. Now, one important feature of a state function is it does not depend on the path. So, what the current temperature is, that does not depend what was the temperature say at some time t1, right? It does not depend on that. So, or what? So, say if I have temperature T1 at time T1 and temperature T2 at time T2, it doesn't matter whether the gas reached this temperature through this path or through this path. What matters is the final value and the initial value, right? So, what you need to understand is a state function depends only on the initial and final values, right? Values does not depend on the path. On the path. Right. So, what will be the examples of state function in context of thermodynamics? Temperature, right? Volume, right? Pressure, all these parameters. Work. Can you tell me whether work is a state function? Work is not. Why? So let's take an example. Work is not a state function. Okay. Why? So let's understand it through an example. Now, say if I have a beaker and there is some gas and a piston. Okay. Now, there are two scenarios. In one scenario, I am putting small pebbles on this one by one. Okay. And this is scenario 1. So that finally the piston reaches some h distance. So the final place of the piston is here. And consider scenario 2. It's the same piston and finally the piston reaches here. But what I have done is, instead of that, I have applied a big block. I have put a big block of mass m. These are of small masses m1, right? So will the work done be same in these two cases? No, right? Because in this case you applied pressure one by one, so work done will add up, whereas in this case you suddenly applied a pressure, right? So here and here the work done, this is scenario 2. Work done in 1 not equal to work done in 2, right? Scenario 2. That's why, which particularly means that work depends on the path, right? And hence work is not a state function, right? Did you understand? How about energy? Yes or no? Is it a state function? Yes, energy is a state function. Why? What my energy is at this point in time does not depend what path did I travel, right? It depends only on what is my energy now. Got it? Okay. So this energy what we are talking about is internal energy. Okay. Is this clear? Okay. Now, once this is clear, I think I have also talked about path function, but let me explicitly talk about it so that you do not get confused later. Path function. So, path function is one which depends on the path of the process. Okay. So, path function is one which depends on the path of the process. Example, work, right, which we will only talk about two functions, path functions, work and heat. So why heat is a path function? So suppose say if you were to, again let's take an example, suppose say this is a beaker, okay, and this is a piston. So this piston needs to be raised this much till this level, or whether this piston needs to be raised till here, okay. The heat required will be different, right, for both the cases. So it depends on how much you want to raise it up. That's why heat is also a path function, right? Got it? What is a path function? Did you understand? Okay. Okay. We have talked about the functions. Now what we'll do is we'll talk about different processes. Or before that, let's talk about properties. Two type of properties of thermodynamics processes. One is extensive property one is intensive property. We'll talk about two types of properties of the thermodynamic processes. Now, what is extensive property and what is intensive property? Extensive property is, it depends, one which depends on the size of the system. I'll explain it to you. What does it mean? Let me first write it down. It does not depend. Now, extensive property is one which depends on the size of the system, whereas intensive property does not depend on the size of the system. Now, what do I mean by size? So, for example, say if I have, say, 500 ml of water, okay, in this beaker. Now, if I divide this into two parts, then each part will have 250 ml, right? So, your volume is a extensive property. Why? So, how do you decide? Basically, if you divide that particular parameter, say, or particular measure into several parts, then its value will change. That is what is the extensive property. So, this gives us an important point to remember of extensive properties, that it is additive in nature. In nature. Right. So, if you divide volume, say if you divide volume in two parts, it gets splitted, right, and when you add, it will become the double of that. Whereas in intensive properties, it does not depend on the size of the system, meaning even if you split, then your particular measure will not get divided, it will still remain the same. For example, say this is water at T degree Celsius, okay. Now, if I split the water into two parts, okay, equal parts, will the temperature of this part and this part be different? It will still be T degree Celsius, right? It does not change. So, temperature is an intensive property. Temperature. Whenever you are given a measure and asked to check whether it's an extensive or intensive property, you can use this particular method. What is the method? That particular, if you divide that particular parameter into two parts, its value gets halved. If it doesn't, then it's an intensive property. If it gets halved, then it's an extensive property. So, can you tell me whether mass is an intensive or extensive property? Mass is extensive, correct. Mass is an extensive property. Why? Because if you split the mass into two parts, your weight will get halved, right? Similarly, can you tell me if pressure is a extensive or intensive quantity? Pressure. Yes, pressure is an intensive quantity. Why? Again, if you see this beaker, if it has a pressure P, right, and you divide it into two parts, the pressure will still remain P in both the parts, right? So, pressure is also an intensive quantity or intensive measure. Did you understand this? Now, one more important thing to remember is, can I rub this? So, when you divide two extensive So, essentially what I mean is, when you divide two extensive parameters, you will get an intensive parameter. For example, your mass is an extensive property parameter and volume is an extensive parameter, right? Now, when you divide mass by volume, what do you get? density, right? You get density. Now tell me whether density is an intensive or extensive property. Use the same method. So if I have water in a container whose density is say 1 gram per centimeter cube, and if I split the water in two parts, will the density change? No, right? The density will still remain as same, 1 gram per centimeter cube. So, did you understand what does this mean? When you divide two extensive properties, you get an intensive property. Got it? Is it clear? Okay. Before I get into the next topic, have you noted down? Okay. Before we get into the next topic, one important measure which I want to talk about is, which is very much used in thermodynamics, either in physics or chemistry, is your heat capacity. Heat capacity. Denoted by C. Now, what is heat capacity? If I talk in terms of a layman, what I would say is heat capacity is the, see, this is some substance, okay, some matter whose temperature is T degree Celsius. Heat capacity is the heat required to change the temperature of this particular block or this particular substance, whatever it is, matter, let's write it as matter, it could be anything, from T degree Celsius to T plus 1 degree Celsius or T minus 1 degree Celsius. Okay. So, essentially what I mean is heat capacity essentially refers to heat required to change the temperature of a system by 1 Kelvin or 1 degree Celsius, right? Depends on whatever parameter you have taken or whatever unit you have taken. Now, mathematically, how do you denote C? dq by dt. What does dq mean? The small amount of heat that you want to give to, and this is the change in temperature. So, amount of heat required divided by change in temperature that you have seen, right? So, this is heat capacity. Got it? Now, can you tell me whether this is an intensive or extensive measure? Why? So, say again, let's think of an example. We have water, okay, and the temperature is T. Now, say if we have a big tank, its temperature is also T. Okay. Now, the amount of heat required for this beaker to convert from T to T plus 1 degree and this tank, will it be same? Different, right? This will be higher because there is more water. That means when you split it up, you require less quantity. When you add it up, you require more quantity. So, this is an additive quantity and hence extensive property. Understood? Important point to remember. Written? Okay. Now, an extension of this are two measures which we will talk about. One is specific heat capacity heat capacity, and the other is molar heat capacity. This is given as Cs, this is given as Cm. Now, what is specific heat capacity? This is the heat required to change the temperature of the system by 1 degree Celsius, 1 Kelvin per unit mass. So, this is the heat capacity per unit mass. So, mathematically what will this be? C that we derived before, heat capacity by M, the mass of the substance, right? Understood? Just give me a second. Yeah. Now, what is molar heat capacity? Molar heat capacity is heat required. As I am writing, you also write along so that you remember. See, you can see this, but unless and until you write yourself, you will not remember it. So, the whole point of me writing it is that you also write along with me so that you remember it, right? Until and unless if we just keep on seeing and not write it, you might understand it at this point in time, but you will forget it after a few days. So, I would suggest as I write, you also keep writing so that you understand and you remember it, right? So, heat required to change the temperature of the system by 1 degree Celsius, 1 Kelvin per unit mole. Do you understand what mole is? Right? 1 mole is a group of molecules together, right? So, this is defined for per mole. That's why it's called molar heat capacity. Cm will be C by N, where N is the number of moles. Okay. This is also extremely important. Now, can you tell me whether specific heat capacity is an intensive or extensive property? Extensive. Why? No, it's an intensive property. What did I tell you? This is extensive, right? Mass is extensive, and if we divide two extensive properties, we get an intensive property, right? Did you understand? So, see one thing, see the beauty of this. Heat capacity C is extensive, whereas your specific heat capacity is an intensive property. Did you understand? Similarly, what will be this molar heat capacity? Intensive, right? Because this is extensive and this is also extensive. Number of moles is extensive, right? If you divide it into two parts, it will get splitted into half. So, this is an intensive. Very important point. So, your heat capacity itself is an extensive quantity, whereas your specific and molar heat capacities are intensive properties. This heat capacity is a very important topic. You are bound to get one question in exam, whether it is NEET or JEE. They test you on this. Did you understand heat capacity in total? Okay. Now, next point that we will talk about is the same heat capacity. Now, what is the definition of, sorry, my bad. What is the definition of heat capacity? Heat capacity is basically the heat required to change the temperature by 1 degree Celsius or 1 Kelvin. Now this can be done at constant pressure also, constant temperature also, right? So we have two types of heat capacity, one at constant pressure and one at constant volume, right? Because we are changing the temperature. So this is called Cp. We are denoting this by Cv, meaning this in this process, when we are deriving this specific heat, we are keeping pressure constant. Okay, and when we are deriving this specific heat, we are keeping volume constant. Okay. Similarly, we can have specific heat, right? At constant pressure, specific heat at constant volume. Similarly, molar heat at molar's heat capacity at constant pressure, molar heat capacity at constant volume, right? This is specific, this is molar. Did you understand? So we have in total 6 heat capacities, right? 3 at constant pressure, 3 at constant volume. Now, since we have done this, I will also touch upon a very important formula which you will see everywhere. C P C M P. I'm denoted in M P C M V is equal to R, where R is the gas constant. You know about it, right? The gas constant. So, to derive your specific heat capacity molar, note that this is the molar specific heat capacity, not the heat capacity, right? To derive this, or to derive the say specific heat capacity at constant pressure given constant volume specific heat capacity, you can use this formula, right? Similar vice versa, right? I will give you some important formulas which you have to remember actually. Secondly, your Cmp by Cmv is given by a constant called gamma. This will be given to you mostly. Okay, and the third one is I will explain you the last formula. First note down this formula. This is very important. What this means is what I will teach you right now. You don't have to worry about that. Yes, TF, TR, TV. Now, what does this represent? This is your translational degree of freedom. Degree of freedom. This is your rotational degree of freedom. And this is your vibrational degree of freedom. I will explain what this means, but I will not do the derivation of this because it's not in your syllabus. It's at a graduation level that you will understand how this is derived. So right now you will have to remember it. Now, what does these degrees of freedom relate to? Basically, so if there is a molecule, right? It might be this way, it might be this way, it might be a single molecule, right? Now, TF, the translational degrees of freedom, refers to in how many straight line directions can the molecule go. So, it can go in X, can go in Y, can go in Z, right? So, this translational degrees of freedom will be 3. Now, rotational degrees of freedom for a single molecule, right? It does not have any rotational degree. So, for a single molecule, your rotational degree of freedom is 0. For a diatomic molecule, what are the two axes? It can rotate around this, right? And it can rotate around this axis, right? So, for this, TR will be 2. And for more than 2, now see, this one can rotate around this, it can rotate around this, it can rotate around this, right? So, your rotational degrees of freedom will be 3 for this, for 3 or more molecules. And vibrational degree we don't consider in normal times, only considered when the temperature is very high. When temperature is very high. And how will you calculate vibrational degree? This will be T vibrational will be 3n minus Tf minus Tr. So, how do we get this formula? Basically, the total degrees of freedom of any, what is n here? Firstly, n is the number of atoms, right? So, in this it is 3, in this it is 2, in this it is 1. So, total degrees of freedom for a molecule is 3n, right? So, total degrees of freedom minus translational degrees of freedom minus rotational degrees of freedom. This will give you the vibrational degrees of freedom. Only but with a caution that it is applicable only at very high temperature. Otherwise, it is not applicable. So, coming back to the formula, did you understand? So, if I were to tell you that find the molar heat capacity at say for a diatomic molecule. So, how will you do for a diatomic molecule? It will be Tf, which is how much? Tf is how much for a diatomic molecule? 2, right? 2r by 2 plus and rotational degree. Sorry, Tf will be for this much 3. Tf will be 3 for all, right? Because it can travel in 3 directions, x, y and z. And T rotational will be 2, 2r by 2, and vibrational will be 0. So, this will be 5r by 2, right? Got it? So, this is for a diatomic molecule. Diatomic molecule. Now, similarly, can you find it for a triatomic molecule? So, this will remain the same. This will become 3r by 2. So, total will be 6r by 2, meaning 3r, right, for a triatomic molecule. Understood? Did you understand the whole thing? This is very important. That's why I was telling specific heat in itself is a very important, heat capacity in itself is a very important topic. You are bound to get one question, if not individually mixed with some topic, you will definitely get a question on this, where you will have to use this concept. Remember that these are molar heat capacities, okay? Dynamics. Next class we will talk about zeroth law of thermodynamics, first law of thermodynamics, and that's where you will start getting questions, meaning you will have to solve problems. So, these are all the basics that you need to solve questions in thermodynamics when you start with first law, second law and so on. I hope this base is clear. If this is not clear, please ask whatever doubt you have, because it is very important to understand this. Have you noted this down? Yes.